Hello to everyone to today's seminar. Our speaker today will be Alex dos Reis de Souza from INRIA in Lille in France. And he received his mechatronics engineering degree in 2018 in Brazil. And currently he's working as a PhD candidate at INRIA. And his research interests include the nonlinear, robust control, robust state estimation, and model predictive control. And also model predictive control is the subject where his current presentation will come from. Now I'll hand over the microphone to you, Alex, and the floor is yours to present your work on robust output feedback MPC using interval observers.
Thank you, Andreas. It's a pleasure to be here to share with you some of my research of the last year. This work has been done in cooperation with my thesis supervisor, Denise Efimov, Tarek Reis from the Conservatoire des Arts et Métiers, and also for the linear case with Xu Binping from the Chilean University. So as Andreas said, the title of my presentation today is Robust Output Feedback MPC using interval observers. So the outline of my presentation today, first we're going to start with some motivation for this work, what we compelled us to do this. I will give you the problem statement, also the assumptions and some preliminaries needed for the development of this work. Later on, we're going to pass through the design of the interval observer and the interval predictor. Give finally the algorithm for the interval MPC, also discuss how it was done for the linear case and also the time delay case. Give some numerical examples in the end and conclusions and perspectives. Good, so let's start with the motivation of this work. Just put the time here, I forgot. Okay, so we know that in practice, we have lots of systems that are naturally constrained. This constraint might be due to physical limitations. For instance, the system might be non-negative. It might be take only non-negative values. We might have physical limitations due to the actuators. They might be saturating. We might have as well constrained as performance requirements. For instance, we have here a bioreactor, a chemical reactor in which we shouldn't let the concentration of the final product be below some level because it might be bad for the production. And also safety. Using the same example here, this chemical reactor, the control input is saturated because it's a temperature of the cooling jacket, and it, of course, it cools down the bioreactor. This temperature can't go over some level because it might be dangerous. It might ruin the procedure and also kill some living organisms that lives inside of the reactor. Another two examples I took here is power electronics. So we have conversion of electricity from AC to DC, or have some kind of efficient conversion between grids. And also something that is very popular today is the platooning. So we have a vehicle here that might take into account adversarial vehicles in the lane. So to take a decision on whether change the lane or keep on the lane, change the velocity and whatever. And okay, since these systems are very recurrent in practice, we have a problem that usual feedback solutions based on Lyapunov methods, for instance, often fail to ensure this constraint satisfaction. And this is why model predictive control, MPC here, has become very popular over the last 30 years, I think, because it allows us to consider a control problem or an optimal control problem that might take a nonlinear system, multivariate, and also, of course, subject to constraints. However, a question that might arise in this idea is that, what about robustness? Because if we use a model to predict the future behavior of the system, this model should be perfect. But of course, it doesn't happen because very often these models are plagued with uncertainty and noises, and these discrepancies, these sources of error will create some discrepancies between what is predicted by this model and what happens in the real system. Furthermore, we might have the problem of unavailable states because we don't measure everything in a system. So this leads to the need of state estimation techniques, and it adds even more uncertainty to this problem because, of course, we have estimation errors. So the question that might arise here is how we can ensure constraint satisfaction and feasibility of this optimal control problem, having some knowledge on these uncertainties. In the literature, we have some classical solutions already that you might have heard about. So we have tubes, tube MPC, either rigid or homothetic. We can rely also on some kind of set membership estimation using for the estimation error. So we know at least a region in which our real estate will B in the state space. We can also rely on MHE, so moving horizon estimation, min-max optimization, which is by far one of the most popular ones, although being a little bit conservative, and also multi-stage MPC that tries to take lots of scenarios and optimize over all of the scenarios. So this is just an illustration of this problem. Imagine that the system is perfect. So the model is perfect concerning the real system. So the prediction and the real system would match. So we have this solid blue dark line here. And we see that if we start in this feasible region, green here, we will go finally to the objective that we want here in the origin. However, this light blue line here looks like that the system is perturbed. So this prediction doesn't match anymore the real system, but this algorithm will be robust because we keep the system in the feasible region and we still drive it to the origin as we want it. However, if this MPC algorithm is not robust, then we might happen that after some steps, the system is driven out of this feasible region, so out of this constraint set. And this point here and on, we don't have feasibility anymore. So we transgress the constraints, and we also don't have feasibility of the control problem anymore. So I'm going to pass to the problem statement given this idea. So I'm going to consider a discrete time LPV system given by the system 1 here. So X are the states and Y are the measurements. A and B depends on some scheduling parameter theta. They are at least known. The function of A and B are known, but theta might not be, as I will discuss in the following. And okay, so we need these first two assumptions. First, WK, which is the process disturbance, and VK, which is the measurement noise, are bounded, and we know these bounds here. And also, the scheduling parameter theta is unmeasured, so we don't know it at any time step k, but we know that it lies in a non-bounded set given by this big theta. Another assumption that is very that's recurrent in the design of I/O, so interval observers, is to say that the initial conditions for X here are bounded, and we also know this bound, given by X0 underline and X0 overline here. Good. The last two assumptions that we need, first, this one is classical in the LPV scenario. It says that the system admits a convex embedding. So we have this A0 and this B0, which are constant matrix, and also this interpolation here using some vertices, delta AI, using a scheduling interpolating function as a function of theta. Good, this is very trivial. And the last assumption might be a little bit strange, but we will take the hypothesis that C, so the measurement matrix, is non-negative. This might be a little bit strange, but this can always be verified since C is constant by a proper change of coordinates, for instance. So the problem we want to solve is the robust constraint control, design and output feedback control for system 1, which stabilizes it and also respects for all times the constraints on the state and the constraint on the inputs. So X and U here are non-convex and bounded sets. And this problem should be feasible for any possible realization of WK and VK, and also the scheduling parameter theta, given the assumption 1. So for our development, we're going to need some preliminaries. So here I show you the first lemma. So basically, it's just to give some interval bounds depending on the matrix A, if it's time invariant or not, and also the state vector X. So if we have AX here, so this is an upper bound if A is constant, and this is a lower bound. And the same holds for if A is time varying. I believe that I have forgotten to put this notation here, but A plus here means that the maximum component-wise of the matrix, so the max between 0 and the value of the matrix, sorry. And A minus here is A max minus A, so just the non-negative parts of every matrix. I'm sorry, I forgot to put this notation. The second lemma we will need is this one by Smith in 1995. So that says that if A is a non-negative matrix and we have a system like this, if omega is non-negative as well and bounded, and also the initial conditions for X is also non-negative, then all solutions of the system will be also non-negative. Finally, we need this third lemma here that says that A is non-negative. It's only sure stable if there is a diagonal Lyapunov matrix that solves this equation. Okay. So now we're going to pass to the design of interval observers and predictors, which are the main core of our idea here. So basically, an interval observer is a two-point set membership estimator. So it's basically a bounding observer. You have an observer for the upper bound estimation and for the lower bound estimation with stability guarantees. It has the form of an observer and some condition designs that look like an observer. And if we can assure that some cooperativity conditions can be fulfilled, then we have this relation here. So for all times, this envelope will be valid. So we have this lower bound in X and this upper bound in X, and of course, X that remains in the middle. So the main idea for our MPC developments today is to use this relation here to check the constraints, because of course, if this envelope here composed by the upper and the lower estimation belongs to the set in which the constraints are, then it's for sure guaranteed that the real state will also be. The main features of this, or what we thought as a good thing for this proposition, is that interval observers have low computational complexity. It's just an observer, and it's very easy to design them given by offline linear matrix inequalities. So let's start thinking about the first observer, so the interval observer. If we use the measurement yk, we can take the first system, so system 1, and transform it like this. It has the same form, but we added and subtract basically LCX. So here and here, and also the measurement. Using lemma 1, so this bounding relations for the matrix A and B, and also under assumption 1, for WK and VK, we can propose this interval observer here. For the sake of compactness of this presentation, I'm not going to show you the proofs, but I'll at least discuss how we can get these things, okay? So basically from this term here and this term here, we get these two terms. As you can see, it doesn't depend anymore on lambda, which is good. And these other terms here are given just by the assumption 1. So it's the upper and the lower bound of the disturbances. And of course, we keep the measurement here. LO is the gain to be designed. So basically, if lemma 4 says that if this matrix here is non-negative, since all of these other terms are non-negative by construction, so under the first lemma, then the estimation errors given by this and this are always non-negative under lemma 2. So the comparative can be seen here because, look, and I also forgot the overline and underline here. So here, I'm sorry. If these estimation errors are non-negative, these two errors will never cross. So we'll always have this envelope giving this upper and lower bound estimation. So this is very interesting. Just to remind, so if A0 minus LC is non-negative, the interval observer can be proposed, which is good because here we only have to prove non-negativity, for this A0 matrix here, because we consider that these other terms here are basically given as disturbances. So to derive some stability conditions for this interval observer, so first we say that it's non-negative. We should prove now that it's stable. We're going to rewrite it as this more compact system here. So basically, this is the diagonal of A0, and this is the diagonal of the gains we want to design. This is given by this matrix here, and also this. And delta here is just given the other terms as other known terms, in fact, because we know everything here. So we measure y, these are given by assumptions, and we know everything. Under this idea, we can propose this first LMI, which says that if there exists some diagonal matrix given by this, and some matrices given by this, we can propose this LMI, and if it's solvable, then the IO4 will be stable. So as you can see, this one here basically say that A0 minus L0 LOC is non-negative, and this one is derived by the Lyapunov stability. So this gives stability for the system. And if it holds, then this relation will be satisfied for all times in the future. Of course, if also all perturbances, so the parameter delta in the previous slide, are also bounded. So here, before I keep on going, I'm gonna present this prototype model just for illustration. So here we have X, we have this matrix here. So we have these two parameter dependencies, so theta here and here, U and WK. We measure the second state, and the perturbances are given by these convex sets here, so this bounded set, sorry. So the perturbances are between -1.1 and -1. And also the measurement noise is given as the same. So the only thing different is that we're going to consider that theta is between 0 and -0.3. And the interpolation functions are given by these two functions here. Okay, so this is a first simulation just to show what we have got with lemma 4 and theorem 1, sorry. So here I'm going to give two steps for this interval observer. So 1 and -1 between 0 and 50 and 100. And as you can see, I select theta here as this function just to show that it can move in time. And we select the disturbances to be given as these two functions here. So as you can see, the black line here is the real system. The blue line is the upper bound and the red line is the lower bound. We can see that it's okay. We have a cooperativity of the errors. They never cross. And the system is very close to the boundaries here. So the interval observer is not that conservative. And if we change the outputs, the inputs, we can see that it goes otherwise and also reaches the lower bound. So it's very nice here. This estimation error here is lower because it's the variable that we measure. So it was supposed to be better. So you can see that it even gets very, very close to the estimate boundaries here. Fine, but we have one problem. Because as I have shown you before, this interval observer depends on the measurement yk. So if it depends on yk, it means that we can't use it for prediction because we can't measure something that is due in the future. So we were thinking about a way how we can implement that using MPC. So the first thing that came to our mind was we need a predictor. But how we can design this predictor? So basically the solution was to propose an open loop framer. A framer is a system that respects this interval relation I have shown you. So the upper bound, that's the real system, and the lower bound, which is independent of yk. But then came the question how we can eliminate yk in this estimator. So here, if we recall that yk is given by this, so it's cx plus the measurement noise, we can rewrite this relation under lemma 1 and assumption 4. So basically, we will take LP. LP here will be the gain of the interval predictor, times ck times zk. Zk is the state of the interval predictor, just not to confuse it with x, which was the one for the interval observer. And we can derive these two relations. So this upper bound here and this lower bound, such that the terms LP yk minus LP vk here can be replaced by the upper relation. So this guy or this guy. In this sense, we can propose this interval predictor. So basically, it looks like much like the interval observer. You can see here that we have some matrix to show non-negativity. We have these two terms here, which are nonlinear. I forgot to say that about the interval observer, but these functions here are the max of 0 and the zk, and also this one is the max of 0 and zk minus zk. These are terms that we know, so the inputs and the disturbances, the bounds on the disturbances. And now, instead of having LPYK and LPVK, we have these two terms here. So if we define again two estimation errors, so here it's good, so I remember to put the good signs. We can show that this system, this system defined by the estimation errors will be cooperative, so they will never cross if this matrix here, A0 minus LPC, is non-negative. The same thing as we did for the interval observer. But since nothing is always perfect, then to show stability of the system is a little bit more complicated. Then we're gonna rewrite it again in a more compact form to derive the LMIs that we need. So we have ZK here as the states of the predictor. This, as before, was just the diagonal of the matrix Y0. LP is the diagonal of LP minus here. Because when we put all of these terms together here, LP and LP minus and LP plus, we're going to see that LP plus disappears. It's going to only be LP minus. And C2 here is given by this. So as you can see, LP minus will appear in these two terms here. A calligraphic plus and minus are the same as for the interval observer, and rho here is just a perturbation that we know, and They are upper bounded and lower bounded by this under assumption 1. Good. So the thing is, this system might be stable if we have a solution for this LMI here. So basically, we have this term for the non-negativity of A0 minus LPC, and P minus C, sorry. No, it's L0 minus LPC, and this one is the stability of this system here. So as you can see before, for the interval observer, we only had U here instead of U plus and U minus. That's because for the stability, since LP plus disappear, here we're going to have only LP minus. So if these LMIs are solvable, they are feasible, in fact, then the IP6 with gain selected by this and this is an IP for system 1. So this relation here will always be valid for all times. And it's also input state stable with respect to this non-disturbance rho, if it's also a bounded signal. So this is just, again, another simulation for the interval predictor, just to make a comparison between the IP and the IO. As you can see, it's a little bit more conservative than the interval observer itself, although I have used the same configuration for the simulation. These bounds are a little bit more far from the real system, but that's normal because we eliminate the measurement, so we can't update this set membership at every instant of time. But here, finally, we can use this. Imagine we are at a time constant k here, 0. We can predict the future behavior of the system and use it for the MPC algorithm, as we're going to do next. Okay. So I'm going to just give some recall on MPC just to make sure that everybody understands it. So first, MPC is going to make a prediction using this model from the at each instant decision k to the future in n steps, which is the prediction horizon. And to prove stability of MPC, we basically need 3 stabilizing ingredients, which are the terminal set XF here. So the interval, the prediction of the MPC should finish. So the end point of this prediction, the last term should finish always inside of this XF set. There should exist a stabilizing gain inside of this terminal set that stabilizes the system. And to use it as an optimization problem, that we should have as well a terminal cost given by VF. So the idea is we should take all of this development we have made for the interval observer in the interval predictor, derive these stabilizing ingredients XF, KF, kappa F, sorry, and VF, and then put them all together to show that the system in the end will be stable. The closed loop system, sorry. So I'm just going to recall here some axioms. This is very classic for MPC. So it's given by Main and collaborators in 2000, I think, 99 maybe. It says that the XF, of course, should be a subset of the state constraints. So it should be inside the state constraint set. It should be, contain 0 inside. And kappa F here, so this terminal gain inside XF should always satisfy the control constraint. So KFX should be inside of U for all X inside of XF. Furthermore, here, this condition says that XF is positively invariant over kappa F. So this is basically a positively invariant set under KF. And if we select here VF, the terminal cost, and L, the stage cost for the optimization problem, I'm going to introduce it later. This system, this VF should be a local Lyapunov function under the set XF. Good. So the idea that comes now is if we need a set, a terminal cost and a terminal gain, how we can design a feedback controller for the IP. Because if we're using the IP to predict the system, as I told you before, using these axioms, the last point of this prediction using the interval predictor should be inside XF. There should exist a gain there that stabilizes the system, and VF should be a local Lyapunov function. To do so, we're going to design a control given by this, so a state feedback control in terms of ZX here, so the states of the interval predictor, the upper and the lower bound, Z, K, plus and minus, W, which is known, so it's just the bounds on the disturbances, and here K plus, K minus, and R are gains to be designed. If we put this in the interval predictor, we're going to have this closed loop system. And these matrices, as you can see, depends as well on the gain that we have decided designed for the interval predictor here, LP. So if we do something that we have done previously, we can propose this LMI. And as you can see here, W1, 2, 3, and W4 relates to K, K plus, K minus, and R. If this is feasible, then the system will be ISS with respect to these perturbances here. Something that I want to recall here to make sure that everybody gets it is that the interval predictor is a nominal system. Then we know everything. We know the states, we know the disturbances, and then that's why we can use it for prediction. And furthermore, using this, we know that it will be ISS for all of these considered disturbances here. Great. But as I told you before, this terminal set, this terminal controller, so the controller that we just developed for the interval predictor, it should also respect the control constraint in XF. One way to do that, okay, we can just assume it, but another way to do that is to further constrain this theorem here. So put a little bit, some additional constraints given by this. Basically say that U is ellipsoidal, so we know a matrix S such that this guy here holds, and also for WK. And if the conditions of the previous theorem plus this corollary here are feasible, then it's ensured that UK computed by the state feedback control I just talked about will always satisfy the control constraint in XF. Good. So basically, now we're in position to state the optimal control problem to be solved. So basically, we're going to define calligraph N here as a sequence of control inputs that will be computed by the interval predictor, by the optimization problem. And we're going to cast a minimization of Vn here that takes into account the states of the predictor and also this sequence of inputs. This cost function is given by Vf, which is the terminal cost, and also a stage cost that will give some weights in every control input and also every stage of Zk. This optimal control problem should be solved under some constraints. So I'll start with 9b here. So here's missing also the calligraphic. So all of the states of the interval predictor should respect the constraints on the state, because if it does, as I told you in the beginning, it's for sure guaranteed that the real system will also respect these constraints. For the stabilizing constraint in the MPC, we say that xn here should finish in the terminal set, sorry. I also made a confusion here. Z here should be computed by the interval predictor. That's why there's X here. I'm sorry, I forgot to put the equation here. So this means that the predictor, the predicted states are always computed by the interval predictor. And the last one missing is this one. So basically it's the initialization of the estimation of the prediction, sorry. At every instant K, we're gonna use the values of the interval observer and the interval predictor to estimate the set membership of the states at the instant K, so we could start with it. And as you can see here, I'm taking a combination of the interval observer and the previous step of the interval predictor for the upper bound and also for the lower bound. And there's a good reason for that. Is that if you remember well, the interval observer depends on the bounds of the measurement noise. If this measurement noise is too big, then it might happen that it's more conservative than the interval predictor itself. So here I just took the same simulations I have done before for the interval observer and for the interval predictor, but here I consider that the measurement noise is given by -0.5 until 0.5. And as you can see, before it was great for the interval observer, they were super close to the real states here, but now, thanks to this modification on this big measurement noise, we can see that sometimes the interval predictor is in fact less conservative than the interval observer. And that's why we're going to take this smaller envelope of estimates to have less conservativeness. Cool. So the algorithm is basically like this. We solve these LMIs. So the LMIs for the interval observer, the interval predictor, and for the controller of the interval predictor. We can select the gains here. This, I think I also made a mistake here. I'm sorry, but this was supposed to be the local Lyapunov function, what we used to compute the control for the interval predictor. So it's going to be our terminal cost or terminal Lyapunov function. And we select the stage costs, so the weights on the every state and every control input like this. We should give the algorithm some initial conditions, so x0 underline and x0 overline, and as well, of course, it's our choice, the prediction horizon n, so how far we're going to look in the future. So online, what we do is we measure yk and we update the interval observer. We use this smaller envelope, as I just said, to initialize IP, and then we solve this optimal control problem under these constraints that I have told you about. If this problem is solvable, of course, we're going to have this full sequence of control inputs to apply. We take the first one, apply to the system, and then we repeat everything. So this is just the classic MPC algorithm, but our interval observer and predictor are incorporated into it. So as a final theorem here, if we take the system, the closed loop system composed of the first system, of course, the LPV system, the interval observer, and the interval predictor, and we apply algorithm 1, then first, we have recursive feasibility. So if it's feasible at the first instant of time, it will always be feasible in the next steps. The interval predictor in XF, so the terminal set, is ISS, and of course, system 1 is practical ISS. And in the end, we have constraint satisfaction both in states and also in the control inputs. Basically here, I'm just going to give you an idea since I don't show you the proof. So this condition here is satisfied by assumption 1. It basically says that this interval prediction is not growing in time. So it's always, it might be converging, but in the end point, it's not growing. So it says that if we start inside this feasible region, the next step will also be inside of this feasible region because this interval is not growing. It can't grow out of this feasible region. ISS here is obvious, is the result I have presented in theorem 4. And the practical ISS for system 1 comes from this interval relation. So if we have this lower bound, the system, and this upper bound, if this envelope is ISS, then we have that the real system inside of this envelope will also be ISS. And also finally, constraint satisfaction is ensured by the optimal control problem and the constraints that we have imposed. Great, so that's what we had for the LPV case. I want to freeze here that we have a multiplicative uncertainty in the LPV case, especially because when we're going to do the prediction in the n further steps, you don't know theta. You don't know theta in future steps as well. And in our case, we don't even know theta in the present time. So it's complicated. This prediction might deviate a lot from this real system. But if the system is linear time invariant or time delayed, as I will show here by this system, here I just put in blue what relates to the time delay just to make this difference, then it's a little bit simpler. The main differences in this algorithm and also in all developments that we have done for the interval observer and for the interval predictor is that first, we can have some optimization of gain, so this LO and this LP, by using the interval width. So basically, we take the size of this envelope composed by the upper and the lower bound, and it depends on L. Since it depends on L, we can optimize L to make it as small as possible. Another thing that is very different is that here we can take this variable here, x star, which is the center point of this estimation. So we take just the mid value, and it doesn't depend on L here for the LTI case. We can design controllers for this variable, and it's much simpler. Another thing that is a little bit different as well for the time delay case is that differently than the LPV and the LTI, since we have delay terms, we should use the Lyapunov-Krasovsky to show that the system is stable and also to have some optimization of these gains LO and LP. In the following, I will show you simulations for the LPV case first. Then, although I haven't shown you how I have developed the LTI and LTD, I'm going to show you some figures, some pretty figures about the simulation of the LTI and the TD case. Before that, complexity. The most interesting thing that I believe is about this interval MPC is that the interval observer and the interval predictor have fixed complexity. So they will never change during the running of the system. This is not true, for instance, zonotopes, because they might grow in complexity, they might grow in dimension. You should add different conditions for this bounding of these errors. And it, of course, requires some harder, not harder, but a bigger complexity, let's say. And if we assume that the number of hyperplanes needed to define x, u, and xf depends linearly on n, so the dimension of the system, and of course we take the worst case here, that the number of the inputs is the same as the number of the states. Therefore, the worst case number of variables to solve this optimization problem is 10 times the prediction horizon times the dimension of the system, so small n. So as you can see, the complexity of our MPC scales linearly with n, big N, times small n, which is very good. Here I just made a small recall that since we're going to use the control, take into account this midpoint of the estimation, the interval estimation, here for the linear case, we have 8 times n times small n. So the complexity is linear in the prediction horizon and also on the prediction, the system dimension, sorry, which is very interesting for real-time applications. So now I'm going to give you the numerical examples. Just let me drink some water. So let's start first with the LPV case. So this is the LPV prototype model I was using to show you the interval observer and the interval predictor. I'm going to define the constraints by this, so minus 12.3, minus 12.3 for both of the states. U to be constrained between minus 2 and 2. Disturbances between minus 0.1 and 0.1. The interpolation functions lambda are given by this. And the only thing that is different than the prototype example that I have shown you before is that now we're going to take theta between minus 0.1 and 0.1. We're going to select x0 here as this. So we're going to initialize the interval observer and also the interval predictor as these values. As you can see, it's okay, it's not a big deal. We're going to select the prediction horizons as n equals 20, a simulation time span of 20 steps, and we're going to run it 100 times just to check if we can move. Actually, we can change theta, change WK, VK to see if the system is in fact robust. So this is the simulation result. As you can see here, this is the unmeasured state. We only measure this guy here. It touches the boundaries of the constraint set in both of them. Here is the control input. So as you can see, we start here at the saturated input at 2, and we go to close to 0 later. And the system is converging smoothly to 0. As you can see here, I also run in parallel the interval predictor to show you that in the end, we can even touch the boundaries of the constraint set. This is very interesting because it shows that this methodology is not conservative. We can get close to the boundaries without compromising, actually without risking transgression of the constraints. I have used the solver fmincon, so it's an active set method to solve this optimization problem. For n equals to 10 here, I had 0.2 seconds with this as standard deviation, and the maximum was 0.77 seconds. So as you can see, for n equals to 10, which is not small, the optimization problem is solved very, very fast. And it's due to the low complexity of the interval estimators I have proposed. Here, as you can see, we have this beautiful flag, which I show you the comparison of the feasible regions for the interval predictor. So if I select the interval, the first states of the interval predictor as this, then the optimization problem will be solved. And here it's interesting that I haven't observed improvement after n equal to 10. So here, these are the feasible regions. As you can see, it shrinks. The smallest is the prediction horizon. This is imaginable in MPC. This is normal. So now for the LTI case, I'm going to use this toy model. So this is the CSTR, so the continuous steered tank reactor. So it's a chemical reactor given by these matrices. Again, we're going to measure only the second state. We're going to have constraints in both of them. We have these disturbances. And here, especially, I'm going to make a small comparison with tube MPC given by Main and all, 2009. For this implementation, I select an LQR controller, so a linear quadratic regulator with these matrices here. And I use quadprog here. So now, since this optimization problem is purely linear, I can use quadprog. So the computation time here is very small as well. So as you can see, 3 milliseconds with a standard deviation of 2 milliseconds. And the maximum was 0.13 seconds, also very fast. This is a simulation. As you can see here, we can also get very close to the boundary of the constraints. The control inputs, actually here, I think it's, oh no, it's okay, it's minus 0.5, 4.5. It's also start saturated, so I'm taking the maximum I can to drive the system as fast as I can to the origin, and also all of these constraints are satisfied. This is the comparison I wanted to do with the tube MPC. So the green area here is the feasible region for the IO MPC I proposed, me and my supervisor and my collaborators, of course. And the yellow ones here are the feasible regions for the tube MPC. So basically I changed how I designed this LQR controller and also the Leuenberger observer that accompanies this tube MPC. And if the selection of these gains are naive, so we don't know very well how to select these terms, then we can see that the impact over the feasible region is quite big. As you can see, first, the IO MPC is always bigger than the tube MPC. But even worse, if the selection of these gains are bad, then we have a very narrow feasible region here. This is due to the conservativeness of the tube MPC in this scenario, of course. Finally, I'm going to present you an example of the time delayed system. So here we have this current state and the delayed state. Also, we're going to measure the second state only. We have disturbances, and the time delay is selected as a known value, h equal to 10. So we are late in 10 steps in the past. We have these constraints, so both of them, and also we're going to select this constraint for the input. So minus 1, 1. Again, disturbances. And here, again, since everything is linear, I can use quadprog to solve this problem. The computational time was 3 milliseconds with the standard deviation of 2 milliseconds. And the maximum, similar to the linear case as it was supposed to be, 0.13 seconds of maximum. So this is also very interesting to see because here, this is not the measured variable. We can get very, very close to the boundaries of the state constraint. Here, we start as well close to the state constraint. And something that I want to highlight here is that, as you can see, the interval predictor is growing a little bit with time. It doesn't mean that it's unstable. It is stable, but it's slowly converging to its true value. It seems that it's a little bit more conservative than for the linear case. And it's also not a problem for the MPC because, as you remember, I take this combination of the IO and for the IP to select always the smallest possible envelope of estimates. Finally, for this system, I can also show that the contra inputs here kicks on the maximum and the minimum. So as you can see, we don't transgress any of the inputs. And as you can see, we stabilize the system at 0 in the end. Here we can even see the impact of the measurement and disturbances noise. It's due to this initialization of the IO and the IP. So in conclusions, we developed some new interval estimators for LTI, NPV, and TD, especially the interval predictors, as well as their respective feedback controllers. So we have both the estimators and both the controller. We took these estimators and we have incorporated them into the classical MPC algorithm. And we have also illustrated some of these applications with numerical experiments. Also, we made some comparison with tube MPC. As I told you before, the advantage of having IO MPC is low fixed complexity. It's easy to design them because, as I shown you before, all of these conditions are given by LMIs and furthermore, offline LMIs. Only the MPC is solved online. And as I have shown you with many figures, many experiments, they show low conservativeness. So it's very interesting. Our perspectives is to enhance the interval estimators to see if we can get smaller and smaller interval estimation, of course, and also see if we can use different techniques to apply these MPC algorithms and reduce even more the conservativeness, or even apply to a broader class of systems. And if possible, also to test its efficiency in some practical scenarios. And that's all for me. Thank you very much. If you have questions, please feel free to ask. And if you want to send me an email to ask something or propose something, my email is on the screen. I thank you very much.
Okay, many thanks, Alex, for your very interesting presentation. And yes, I would like now to hand over the microphone to the audience to ask questions.
Pleasure.
Who wants to start with the first question?
I want to see some faces.
Okay, as no one has raised his hand so far, let me start with something. Could you go to the slide number 8, please?
Yes, of course. Yeah.
Yes, because the thing that you had shown there for the linear parameter varying case, I think could quite easily also be used in the case that your system matrices A and B depend on the actual state information. You would have some A of X and B of X. Now, the question that came to my mind when looking at the equation is, do you have any idea how to find, let's say, a kind of optimal quasi-linear state space representation? Because usually this A of X and B of X, they result from factoring out state information. For example, if you have polynomial state equations from the nonlinear expressions and find some A of X or some B of X, and this is usually not unique. Do you have any idea how to perform some kind of, let's say, least conservative representation? Okay, what is obvious is you need a representation that is controllable, that is observable.
Yeah. But sincerely, no, I don't. Because actually that's what we assume here in assumption 3, that we at least know these vertices of this polytopic system.
Okay, that would mean maybe that's also a further interesting point as an outlook for future work to optimize such kind of polytopic uncertainty model.
Yeah, but then it falls more in the framework of having LPV systems, like LPV system itself, not MPC interval observers, right?
Yeah.
Yeah.
It's maybe a one step in advance finding an optimal model.
Yeah, I understand.
Yes, and since I do not see any questions so far, I have a second one. You assumed in your scenario that the time delay was known.
Yes.
Do you have any suggestions what to do in the case that your time delay may be temporarily varying and you don't know the variation rate?
Actually, me and Dennis, we have discussed it, and it's much more complicated because to prove that the system will be non-negative in the end and also stable, it's much more complicated.
Yes, but you don't have any solution.
No, not yet. Actually, if you take like the book of Emilia Friedman, for instance, you see that there are lots of conditions for stability of this kind of system. They might even be unknown, but time varying as well. But when you're going to put it in interval observers, then it gets a little bit more complicated to show that the system will be non-negative.
So I think for a pure simulation, this would work. I did something related to this recently, but I think in the observer framework, that's really getting tough.
Okay, but I haven't tried that yet. Maybe something for the future.
Yes, and another question, you proposed the thing that you called interval predictor.
Yeah.
This introduced yes, some additional gain information. Now let's assume you do not have this LP. You're just performing a parallel simulation of your system model. Maybe you're transforming your system model in advance before doing the simulation into a set of coordinates where the dynamics are cooperative.
Yeah.
do you have any, let's say, kind of gut feeling in which scenarios your predictor is less conservative than just performing a parallel simulation? Or are there maybe scenarios where pure parallel simulation is more efficient than your interval predictor?
Well, if I remember well, there's a work on MPC given by Camacho and Limon, I think, that they say that if we can do the simulation, even if it's open loop simulations for the worst case of the system, so the highest and the lowest scenarios, then the MPC would work. But the problem is showing that this prediction will be stable. Because let's say that if this prediction, as you're saying, using this parallel system diverge after 10 steps, then the optimal control problem will never be feasible.
Yes.
It will never finish inside this XF, which is a requirement for stability of MPC.
Yes, that's something that is obvious. The open loop dynamics must be stable.
Yeah.
And yes, also you have to find bounding systems that are not overly conservative.
Yes. Yeah. And I believe, I'm not sure, but what could you get here that's less complex than this? It's just an observer. The complexity is proportional to the size of the system. It will always be for any kind of propagation.
That's true.
Yeah.
Okay, do we have any further questions? Yes,
Why
there's one question in the chat. Can you ask your question, please?
I have a question.
Yep.
Why do you make the assumption 4? Is that crucial for you to design? Can it be removed for this constraint?
No, actually, we needed to propose sorry, let me put it back here. This, because if C is changing signs here, then we can't say that this holds for all time. If C is changing sign, then you might have negative values and positive values here, and then these inequalities here will be inversed. But the thing is, this assumption 4, you can always verify it. Sorry, where is it? Here. You can always verify it by a change of coordinates, because C here is not time varying.
My question is, can it be removed for this constraint? I think it is a constraint. So all your design is under the assumption of this assumption 4.
Yes.
Okay.
So the answer is no, because we should prove non-negativity of errors, and this is needed.
Okay, thank you.
Okay, I see a further question in the chat, and the question is, for your simulation, can you increase the system dimension?
Yes, of course. As long as the LMIs are feasible, you can have a system of any other as you'd like. We have no constraint on the system dimension. As long as the LMIs I gave you are still feasible, you can do it.
Yes, and I also think computing time for solving the LMIs is not crucial, because that's something that is done offline.
No, yeah, and especially these ones are solved in less than 1 second. This is very, very simple. And this is one of the advantages of our method. You have this list of LMIs that if they are all feasible, then the solution of the problem exists. If they're not, then we don't know. Let me just chat here.
Hi, Alex. I have a question. Could you please go to page 21?
Yes. 21. Yes.
I see the second and the third terms on the right hand.
Yeah, so this one.
Yes. Are you sure these terms are the upper bound of delta A multiplies the key?
Yes. Actually, I didn't show it here, but in our paper, if you want to see it later, here, if you remember, these terms relate to the sum of lambda I theta times the vertices of the system, times x, of course. So first we take this lambda x, we find an upper bound of it, then we use just this interval bounds of delta. Here, I also forgot to show you that, but still, this delta A plus here, delta A minus, is the sum of all of these vertices.
As far as I know, because delta A is unknown and zk is also unknown. As far as I know, delta A multiplies zk should be bounded by the sum of 4 terms.
Yes. So first, delta A is unknown, but you know its bounds because you know this polytope. So you know all of its vertices, right? So basically, delta A plus here is the sum of all of these vertices taking its non-negative values for here and here. Lambda, which is the interpolation function, is bounded between 0 and 1 because it's convex. So you know that the lower bound is 0 and the upper bound is 1. So if you have lambda times x, I should have shown it here, but there will be lots of space. But still, you can show that this is between, for instance, minus x overline and above x overline. After that, you multiply by this matrix here, which is the worst case of all of the vertices. So that's for sure guaranteed that this is positive, non-negative, sorry.
For this problem, I'm not sure. I'm not very sure. Please check it.
Well, as soon as I made the article available, I can show you. Thank you for the heads up.
Okay, thank you. And I have another question.
Please.
Do you consider parameter uncertainties in the controller design?
No.
Oh, okay,
No.
okay, thank you.
No, actually, here, as you can see, we take it into account in delta B. This is uncertain. But if you look at the LMIs of the control, here somewhere, not this one, sorry. This one, they are affine in the control. So if you can solve this LMI here for all of these vertices, then you can have as well some kind of scheduling controller.
Okay. So you have to solve a series of LMIs. Okay.
Here, just to streamline the presentation, we say that d delta B is equal to 0 just to make it smaller. But there's no problem because you can see the LMIs are fine. Okay,
thank you.
Okay, we have a further question in the chat from Xubin Ping. Maybe you,
hello, Xubin.
maybe you can ask your question yourself.
Yeah, if you have a microphone.
Okay, he's still muted. Maybe let me read the question. Why did you consider ellipsoidal constraint sets for the input and state constraints? How about the results when polyhedral constraints for the inputs and states are considered? It seems that the simulation results are about polyhedral constraints for the states.
Yes, but actually here, as you can see, for instance, the examples, let me minimize this. We have, sorry. Here, these are okay, this is ellipsoidal, but this is not, this is polyhedral. So there's no problem here. We can have this constraint set should be polyhedral. The only thing that we assume that our ellipsoidal is here when we're gonna make sure that the U actually impose that U is ellipsoidal, and here that Z, so the set of disturbances are also ellipsoidal. This is the only thing that's needed. But for the optimization problem, there's no need for that. Of course, here U should be ellipsoidal to show that the input constraint will be satisfied inside this ellipsoid, because our XFs or our terminal set is an ellipsoid. I don't know if I responded well, but
no, we don't have a response. Thank you. Okay.
Thank you.
Do we have any further question?
We can see the participants. Oh, lots of people.
Okay, no further question from the rest of the audience.
Maybe I've got a question.
Yes, please, Elena.
But I have not so large vocabulary in English. In what how did you decide these kind of equations in this slide? For example, this matrix is non-negative defined, yes?
Yes, it's positive, the semi-definite, I think.
And in what program did you decide this kind of equations?
Ah, you mean in which software I solved this LMI?
Mm-hmm.
It was the YALMIP. This is the simplest one, the most famous.
I tried.
YALMIP is the interface, but which solver did you use?
Ah, which solver? Oof. I don't remember. Maybe it was QuadProg. Probably was QuadProg. It's linear.
I tried to solve these questions in MATLAB.
Yeah.
But this but MATLAB uses only positive defined strong strong condition, not
No, but you see, this is not a problem because this matrix should be equal or greater than 0. If it's only greater than 0, that would be a problem numerically, but YALMIP handles it very well. Maybe it's just the way you have defined your variables.
Mm-hmm.
Because I think the only thing where you should be really careful when using MATLAB for solving LMIs is I do not recommend to use the built-in solver LMI lab.
Yeah, no, that
yes, but everything else I think should work quite well.
Yeah. YALMIP is a gift.
Yes.
I have another question. Okay, sorry.
I thought our seminars began at 1 o'clock. Yes.
Yes,
Yeah.
but I think maybe you didn't bear in mind that the west of Europe changed to summertime already.
And I plus 6 hours and
yes, you next time you should log in 1 hour earlier.
Yes. You did you send запись, как же, record of these seminars?
Yes, it's recorded and I'll put it on YouTube.
Do you really understand me?
Yep.
Yeah.
Yes.
Okay, do we have any further question?
Anything else? I would be pleased to respond. So I before finishing, I would like to thank Denise Ifimov, Tarek Haisi, and Shubin Ping for our collaboration. It has been very fruitful and I have learned a lot. If anyone here has some kind of request, any suggestion, anything, I left my email on the last slide and I would be very pleased to respond to you as fast as I can.
Okay. I think these are already quite nice concluding remarks. If no one else has a question, I would like to thank you again, Alex, for your very nice presentation, for answering all the questions. Also, thank you very much to the audience for attending this seminar. And yes, the only thing that is left is I wish you a nice Friday afternoon, evening, and weekend, as usual, and see you again in 2 weeks. And since I see it here in the audience, our next speaker is also present today. Our next speaker will be Sylvie Puteaux from Paris. And yes, thanks again for today's talk, and see you again in 2 weeks.
Ciao.
Thank you, Alex, for